Okay, so this is the last lecture, and it's essentially trying to wrap up Gaussian processes, the stuff that I didn't manage to say last time. So I'll start by recapping quickly where we left off last time, and just a quick summary on sort of key things from last time. And then the main thing today is to discuss covariance functions of Gaussian processes. So that's the key idea. And so we'll do that. We'll discuss the difference between working with noisy and noiseless data. And we'll end by me just giving you some pointers to sort of further literature on what I think is interesting GP stuff. For instance, the connection between Gaussian processes and infinite neural networks, which is kind of a cool concept. So today is Monday, May 9. So to recap, we're looking at Gaussian processes, and we're doing it in a regression framework. You can also use GPs for classification, but we're focusing on regression. And conceptually, the way to think about Gaussian processes is as probability distributions on a space of functions instead of a space of just numbers. There's probability distributions over possible functions. And even though functions are infinite dimensional, we will only ever ask finite questions of them. So we will only look for posteriors and prior probabilities on a finite set of function values. And that's why this becomes tractable in the end. So as we discussed last time, I will not repeat all the various notations, but our starting point was a probability distribution looking like this. So f star is the unknown function value at the point x star, which is the test point, the point we're interested in making a prediction for. And f vector is a vector of what will be our training data. So these are known function values, but currently at this point, we haven't looked at them yet. So this is now our joint prior probability distribution for both the test point and all the training points. And we will assume that the input points are always known. So the input points is x vector star. So the input space is high dimensional. So that's why I use x vector. But this is one point in this high dimensional space. And then the collection of all the input points of the training data is then, say, n different. If x vector is m dimensional, then and you have n training data, then you have n m-dimensional vectors, which you can organize in a matrix, which we just call capital X. So these are the input points of all our training data. So what this is a joint prior for all, let's just call them relevant function values. So yeah, f of x is our is the true unknown function. And our goal is to get a posterior prediction for the one unknown function value that we're interested in. So we're looking for, and then having learned the information in the training data, so then this looks like given the information here and all the information we already knew. So this is our posterior prediction for f star, which is just defined to be the true function at this input test point. after having learned information in the training data. And in general, this is, if you want to use completely general PDFs, this is intractable. But if you start from the point of GPs, is to start from a Gaussian prior. And then you end up with a Gaussian posterior. So both these probability distributions will be multivariate Gaussians. And this makes this feasible to actually do. So you end up with a Gaussian posterior, meaning that this posterior distribution, which is now, if this is just a single value, a single test point, then this is a one-dimensional posterior distribution. So this is just now a normal distribution. And being a normal distribution, it's defined by some mean and some variance. And the key point, the key equations from last time is that we know mu star and sigma star squared. We know the mean and the variance analytically. Because these are normal distributions, we can write this down analytically as a function of the mean and the variance of this multidimensional Gaussian prior. So the key equations in GP regression is that mu star is this function m at the test point, and then it's this kernel function or covariance function k x star, which is 2 inputs. Then it's the covariance matrix of the prior or of the training data, inverse of that. And there's a bracket taking the difference between the actual training data and their prior means. And sigma star squared, so the variance is k x star x star. So that's our prior variance, and then it's reduced by an amount given by our choice of covariance function. And I mean, it's reduced from the fact that we learned some more information from the training data. So the variance has to be lower than our prior variance was. So it looks like this. So this is, let's call it central prediction, and this is prediction uncertainty, or the variance. So the square root of this would be your one standard deviation uncertainty. And this function m, and which takes one input, and this function k, which takes 2 inputs, they are the mean and covariance functions that we chose to define. So when we started from this prior to specify this, it has to have since it's a multivariate normal distribution, it has to have a multidimensional mean vector, giving the mean in each direction. And it has to have a covariance matrix, giving all the covariances of all the variables here. So we need to fully specify our prior, we need to specify this mean vector and this covariance matrix. And the way this is done in GPs is that you do it indirectly by instead choosing a mean function, m, and a covariance function, k, such that if I give you any input point x, you plug it into your mean function, and that's your prior mean at that point. And if I give you 2 inputs, say x vector and x vector primed, then you can evaluate the covariance function, and that gives you that element of the covariance matrix, which would then correspond to the covariance between f of x and f of x prime. So the key thing to remember here is that even though these functions are chosen as functions of your input space, the values represent means and covariances in F space, right? They're functions of X, but they're means and covariances in F space. So we chose these functions to define our the mean vector and covariance matrix of our prior and this so all this notation is in the notes from last time, but just to remind you, this sigma matrix is the part of the covariance matrix, which is just the covariates between all your training points. So this is most of the covariance matrix of this prior. So this is effectively where we left things last time. And what we'll see today is that the main sort of modeling step in GP regression is precisely choosing this covariance function, which is the key function to choose, because that ends up defining your prior belief on function space, and then what sort of conclusions you draw as you get data and move towards a posterior on function space. Notice that so far we have assumed in these expressions here, we have assumed that this mean function and this covariance function are fully defined. There is no sort of unknown parameters in these functions at this moment. And that's what will change now. Now we'll say that actually we're not going to choose those functions 100% specifically. We will choose some parameterized functions. And those parameters are then the hyperparameters of this method. So what we're getting to now is how to choose and optimize covariance functions. And I will use covariance functions and the word kernel interchangeably. And this is both the sort of design step, similar to how you would choose some structure of a neural network, for instance, and your results would depend on the structure of the neural network. Here we choose covariance functions. And optimizing these hyperparameters is then the training step, effectively, of this. So the covariance function, what it does is that it encodes our prior expectations about, so encodes prior, let's say, knowledge about this function, f of x. And it can be things like, do we expect, how smooth do we expect this function to be? Do we expect it to be periodic? What's the sort of typical length scale? So is this a function that varies very quickly, or is it a function that varies slowly? And sort of what's the typical length scale of variations or of a period, if it's a periodic function? Does it have some sort of increasing or decreasing trend? Is it symmetric in some way? Perhaps it's symmetric around the origin, something like that. So this is really where the prior knowledge that you have as an expert on whatever field you're using this on, right? This is where you try to encode that without ever writing down, oh, I know this is, the true function should be a third order polynomial, right? If you already knew that, then perhaps something like Gaussian process regression wasn't necessarily the tool you needed, right? Because this is a non-parametric method. So it's trying to help you in cases where you don't, you're not guaranteed to know the exact function form. So the common approach then is to choose a kernel function. So the kernel function is much more important than the mean function. The mean function is very often just taken to be a constant. Constant at 0 or constant at the mean f value of all your training data. You're of course free to choose whatever function form you want, but it tends to be completely, the impact of it tends to be completely swamped by the information in the training data. The exception to that is if you try to extrapolate your Gaussian process model far beyond the end point of your training data, because at that point, the further you move away from the region where you have data, the more your prediction will be dominated by the prior, right? Which is sensible. As the data becomes weaker, you tend towards your prior prediction, and in the end, you'll just predict your prior. So if you chose a constant prior at 0 as your mean function, your prediction will just be 0. So okay, it does matter, but as long as you have some data, it tends to matter not too much. So the common approach then is to choose some kernel functions with some parameters, and then to choose those parameters by doing a maximum likelihood fit. And that's the training step. But before we actually discuss that, let's discuss why that is sort of an un-Bayesian thing to do. So this is a fundamentally Bayesian approach to regression, right? And if you have unknown parameters in a Bayesian framework, typically you don't try to just choose a number for them, right? Instead, you say, if I'm uncertain about something, I should express it with a probability distribution, and I should integrate them out. So that's the most, so let's say, common approach, which is, I mean, what most people, including myself, actually do in practice. Common approach, choose parameterized kernel function. So that's step 1. Step 2, what did I say? Fit parameters in a maximum likelihood fit. And this is the training, quote unquote. But let's note that this is un-Bayesian.
It also constrains yourself to a specific class of kernel unit, right? Like you basically just optimize within that class of kernels, let's say, but you don't get a handle for it. If is the structure of your model really good compared to any other model? So I guess you would also have to do like a model comparison to really want to do it properly, right? But you sort of find yourself to this
Yeah, so it's very much a sort of continuous spectrum here, right? From the sort of being as specific as possible, which would be I'm choosing this kernel function and I'm fitting the parameters to this value, and that's all. And then going, say, one step in the Bayesian direction would be, as I'll write down now, it will be actually I'm going to choose a prior distribution on my hyperparameters, still using that kernel form, but I'm going to integrate out these parameters. But of course, then you could also say, actually, I'm not just going to consider that kernel, I'm going to consider some mixed kernel or something else, and I'll do a model comparison. So you can go more and more general. Yeah. But of course, the more uncertain you allow yourself to be about this, in the end, what it amounts to is typically to increase the uncertainty in your prediction, right? So you can end up being overly conservative to the point where if you allow yourself to be so uncertain about this prior function, right?
Then in the end, you still get an error for your uncertainty, right? So it's like you have an idea of how uncertain you really are, whereas in this case, you basically set it for a set of parameters.
You do, and what you're saying is a very interesting point, and it's actually one of the sort of the last points on my lecture notes is what goes wrong because of this, because actually something goes wrong. So your intuition is something goes wrong, but everyone still does it. So let's say what we should do is assign prior for the hyperparameters and marginalize or integrate out those parameters. So if we say, so I'll use theta as the hyperparameters. So then our GP posterior should be, so it should be what's our posterior belief for this unknown function value, given what we learned from the training data, and we know the input point. But actually, what this should be is this joint distribution of P of F star and the hyperparameters given the training data and the input point integrated over all our hyperparameters. So this is saying I should have had the joint posterior of my function value and the hyperparameters, and I should integrate that posterior over the hyperparameters. We can rewrite that then as P of F star once you've given a specific hyperparameter and training data and input points. So this times this. So just a 1D posterior for the hyperparameters. And this is then proportional, I'll just exchange this hyperparameter posterior with the likelihood times prior. And neglect a normalization constant. So this first factor is the same as before. And GP notation is tedious to write. So then it's this function here, which is now the likelihood, or at least if you read it in as a function of this hyperparameter, it's a likelihood function, and here we'll have times our prior on these hyperparameters. So this is what we should have done. And you see here we could have chosen a prior, P of theta, and for every choice of theta, we have a likelihood function for saying, okay, for that choice of theta, how likely was the training data? So that's this factor here, right? And we could perform this integration and actually get a GP posterior that was marginalized over hyperparameters. But this is computationally expensive. So you typically don't do this. So computationally expensive. Common approach is to choose point estimate for data. That was supposed to say, namely, value that maximizes the likelihood, which I'll call L of theta, which is now this factor P of F bar theta x, now interpreted as a function of theta. And what it will be is that this will be a normal distribution with this mean vector and this covariance matrix, but this covariance matrix is now a function of the hyperparameter of your kernel function. So this approach of allowing yourself to fit the hyperparameters like this, sometimes it's called empirical Bayes, because it's sort of effectively you're taking what should have been your prior, which was this original GP defined by a kernel function. You're using the training data. So you had the prior, it was supposed to be a joint prior of test point and training points. But then you're looking at the training points in choosing the kernel function that defines your prior. So you're peeking at the data to make a wise choice for your prior, which is sort of circular and inconsistent, and it's called empirical Bayes, but it sort of works in practice to a large extent. So it's a little like we're peeking at data at training data and effectively choosing a delta function prior and choosing prior, let's say delta. So our prior for these hyperparameters are then effectively a delta function, which is just choosing this maximum likelihood point. So this is where this is effectively your intuition, right? That instead of taking account to some sort of spread in hyperparameter space by doing this, you're putting all your eggs in one basket, which is a single point in hyperparameter space. And this will come back to bite you in the end. This log likelihood, since this is just this multivariate, the likelihood function is this multivariate Gaussian, what you typically maximize is the log likelihood, right? So maximize log likelihood, which is now -1/2. And then it's f vector minus m of x transpose inverse of this matrix. And remember that this is now a function of your hyperparameter f minus m of x. And then there's a couple of more terms. There's -1/2 the logarithm of the determinant of the covariance matrix. And then finally, it's just a constant term, n squared, no, n half ln 2 pi. So n here is the number of training points. So it's the dimensionality of this multivariate Gaussian. Of course, this last term doesn't actually depend on the hyperparameter. So that term isn't important to find the maximum, right? Because it won't change anything, but it's mathematically still there.
So like nobody is guaranteeing us that cost function has only a single peak, right? So you could have many peaks.
There will be many peaks. Yes.
So in the end, we just choose that set of parameters that gives us what the maximum Not likely.
And crossing your fingers that you actually found a maximum.
Okay.
Or at least that you found a decent. I mean, there will probably be a global maximum, right? But how are you sure you found it? So the more complicated your kernel function, complicated in the sense having more hyperparameters, right? The more high dimensional this hyperparameter space becomes, and you end up with a difficult optimization problem in hyperparameter space to train your GP. And when we discuss this noise versus noiseless case, you'll see a very common example of a case where there's at least two optima in hyperparameter space, where one optimum corresponds to the GP assuming very little noise and say a short length scale, so going through all the data points. And another optimum in hyperparameter space is assuming a long length scale, so very smooth functions, but with a lot of noise. So it just captures all the training points within its noise band. And both are sort of valid inferences, right? But typically you're mostly interested in one of them, not the other. So note that for every point, as you try to optimize this function, you walk around in theta space. And at every point you have to evaluate, at least if you just read this naively, right? You have to evaluate this inverse matrix as a function. So for every point you sort of have to invert this matrix. Standard techniques for matrix inversions go as n cubed. You can, if you look in the Rasmussen and Williams book, algorithm 2.1 in that book is sort of the standard algorithm that everyone refers to in this field. And there you'll see a way of using Cholesky decomposition. So you get the cost down to an n squared effectively. But still you can see that this becomes very challenging as your number of data points increase. So n is the number of data points or training points, right? So the sort of rule of thumb is that naive GP regression starts having trouble for more than order 10,000 data points. Once you get to 100,000 data points and more, you start to struggle typically computationally. And there are ways to go beyond that, but then you have to start working with some sort of more clever tools. Right, so now let's actually start discussing kernel functions. And I'll list two very common kernel choices, and we'll browse a couple of web pages which have examples of more. And we'll discuss how to combine kernel functions. So the standard one that everyone starts with is the squared exponential kernel, or Gaussian kernel, or whatever you want to call it. Squared exponential kernel. And it's defined like this. So you have two input points, just call them x and x primed. So it's what it says on the box. It's a exponential, and so it's precisely as a Gaussian. Looks like this. And then one of the hyperparameters is L squared, taking the role of the variance in a normal distribution. And typically you also put a sigma f squared, an amplitude in front here. So the hyperparameters, hyperpars, are L and this sigma f squared. So what is this function saying, right? Remember that the meaning of this function is if I give you two input points, x and x prime, this function is supposed to return the covariance between f of x and f of x. So this function is returning effectively how correlated, right? Because covariance is proportional with correlation. So how correlated should f and let's call it f prime be? And what this function is saying is that, well, if the two input points are the same, right, then this exponential is just exponential zeros, it's just one, so it'll be perfectly correlated. If the distance between those two input points, as the distance increases, the correlation between those function values should decrease, and it should decrease as this exponential. And how quickly should the correlation fall off as you take these 2 points and move apart? Well, it should fall off. How quickly it falls off is given by this length scale. So what this is saying is that if you let this L be large, then the correlation will fall off slowly, meaning that points that are function values that are far away from each other in input space still are fairly correlated. And this is a way of saying that you expect smooth functions. But if function points are very uncorrelated, that means knowing this point tells you very little about this point. So then you get functions that can wiggle quickly. So this is what's called a universal kernel. What that means is that this is sufficiently flexible that if you give it enough training data, a GP with this kernel can learn any function form. So it's universal in that sense, but that doesn't mean that it's necessarily very efficient at learning the function form. But at least in the limit of infinite data, this kernel will learn your function form. It's a bit like how infinite neural networks are sort of universal approximators, right? That they can, if you just have enough, have a general enough network, you can approximate anything.
You also have multiple length scales there, right? As in, like in X, Y, and Z direction, there's two different lengths.
Yes. So we'll get to that, but what I'm giving you now is effectively some kernel basis functions, but typically you end up combining kernels, and you can multiply kernels, you can add kernels. So if you had, this was x1, x2, x3, and you expected very different length scales in those directions, you could have a kernel that was just this kernel in the 1D version multiplied 3 times, right, for x1, x2, x3. Of course, the challenge then is that suddenly you have 3 hyperparameters, L1, L2, L3, instead of just L. So it gets more complicated, but it's very common, right, that you have parameters with widely different length scales. So this kernel prefers very smooth functions.
Sorry about that. Like if I just multiply 3 of these great exponential kernels with different values of L, that would not be the same as assuming that the characteristic length state in X, Y, and Z direction is different, right? Because you just, I mean, you basically say that if I write down that kernel as it is written right there, I say that the characteristic length state of the sort of the distance between 2 samples should be L. But it does not say, like it could also be anisotropic, right? And then just multiplying them would not be the same thing as, for instance, having a diagonal matrix in the exponent with 3 different values of L.
I'm thinking.
I might be also wrong now, but
So say the first thing you said again.
so if I understand that squared kernel correctly,
Mhm.
L just specifies what is the characteristic length scale of the distance between x bar and well x, right?
Mhm.
But that's intrinsically isotropic. I don't like pick out a certain dimension in space that has length scale L1, let's say.
Mhm.
If I now just multiply that squared exponential term with another one, I say, well, I have two characteristic length scale in R direction.
Right. Yeah.
But that's different from saying I have one characteristic length scale in X and one characteristic length scale in Y.
Yeah. So what I was talking about was doing this.
Yes, exactly.
Dividing up the components.
Yes.
Yeah. Right. Yeah. But what you were saying is that, well, you could also imagine creating a kernel which is isotropic but combines different length scales.
Yes.
And you end up with a different type of kernel, which is sort of an infinite sum of these, or I think it's a sum.
Yeah.
Okay. But yes, good point. Okay, let's take a quick break here. I suggest that we do just 10 minutes break, if that's fine with you. Yeah, cool. Okay, so let's get back to this. So this squared exponential kernel has two hyperparameters, the length scale that we discussed, and this sigma f squared is the scale factor. And what it does is effectively it sets the average distance that your function can vary away from the prior mean function. So it just effectively sets amplitudes of wiggles in your functions. So scale factor and L is in scale. And let me try to show you. So here I'm just looking at the documentation from scikit-learn for Gaussian processes. And they have a chapter kernels for Gaussian processes. And this here they do general sort of radial basis function kernels, but as you see, this is exactly the squared exponential that we're looking at if you just take d to be the distance, the difference between them. So, and then this is examples of, okay, say you chose a prior mean of constant at 0, then this gray band is sort of your one standard deviation uncertainty in your prior, the width of your prior. And then these sample functions are samples from this prior over function space. So by choosing the squared exponential, you're saying that my prior degree of belief is that the true function should be a very smooth looking function like this. And then if you learn some data points, then you get a posterior like this. Again, you can draw samples from the posterior. So it favors very smooth functions. But of course, L sets the length scale. There's another important property of this kernel, and it's the fact that it's what's called a stationary kernel. And what this means is that it doesn't change across input space, right? This is a kernel that's only a function of the difference between two input points, not their actual absolute location in input space. So, so that in that sense, the kernel is stationary across all of input space, whereas a kernel that would actually change depending on whether you were far out or close nearby to something in input space, that would be a non-stationary kernel. The second kernel I want to actually write down, and then we'll just look at some of the others, is what's called, it's a generalization of this, and it's called the Matan kernel. And it has a very funny looking functional form. So it's 2 to the power 1 minus nu. It's the gamma function of nu. There's a bracket, square root 2 nu, absolute difference x minus x prime. So again, this is a stationary kernel because it only depends on the difference between 2 points, not their absolute locations. This is to the power nu. There's a k subscript nu, and there's 2 nu x minus x prime, absolute value L. So it looks terribly complicated. Again, so this has hyperparameters nu L. Note that I could have put a scale factor in front of this as well, like before, like the sigma f squared. Typically, you would do that, but you wouldn't, if you were combining these kernels, you wouldn't have one scale factor for each. You would have just a common scale factor in front, at least if you're multiplying them. So R is the gamma function. K nu is the modified Bessel function. Common choices for this parameter nu is, so common choices is nu equals 1/2, 3/2, 5/2. And the point is that nu sets smoothness, and when nu goes to infinity, we get the squared exponential kernel back. So the squared exponential kernel gives you functions that are infinitely differentiable, whereas this gives you functions that are not infinitely differentiable, so less smooth functions, unless you take the limit where nu is infinite. So as you take nu towards infinity, you get smoother and smoother functions. And what these then look like, so here, again, in the SciPy documentation, you have this written out for the cases with nu equals 1/2, 3/2, and 5/2. And these are sort of the examples that you see, okay, you get functions that are a bit more erratic in a sense, less smooth. In practice, so for my applications of GPs, I've very often ended up with a Matan kernel. It is proven, at least for my use cases, really, really useful. So it's sort of my go-to kernel.
How do you compare the result of two functions to that composition comparison? Do you just look at the value of the marginalized likelihood to just see what would maximize that metric, or like?
It's a difficult question. It really is. You can do model comparison properly, but even that gets tricky because it's a sort of a global property. I mean, in the end, you take test cases where you know what is actually the true underlying function, right? And you compare them and see which choice of kernel seems to best capture this function with the sort of quote unquote correct uncertainty. But this is, it's super difficult. So for instance, in the one paper I've done where we used GPs, we trained the GP to do some particle physics calculations. The majority of that paper is us trying to convince the reader that actually this choice of kernel and this trained GP captures the true function across all its input space. Because one thing you will often find in a lot of machine learning papers is that, okay, they give you some sort of error histograms, right? Where, okay, you sampled a bunch of test points and you've evaluated what was the error between your machine learning prediction and the true value. And then you give a histogram of those errors. And if that histogram is narrow, you say, this works. And I've tested it because I've sampled a lot of points. But that histogram, again, is a global, is a way of trying to summarize something over all of input space. One thing you will not learn from that histogram, for instance, is whether perhaps your function works very, like super well in almost all input space, but then in some special region, you're systematically way off. So that perhaps all those what looks like few points out in the tail of your error histogram, actually it's one local region in your input space and where you're really, really wrong. And if you at that point assume that, oh, my model is in general very good, you'll do, yeah. But this is problematic, right? Because the problem you were trying to solve in the first case is typically that you cannot afford to evaluate the true function in all regions of input space. So it's just very, very difficult. Okay, so this was the Matan kernel, and what we'll do now is that we will just look at some other kernels, and there's a very nice, simple, very nice web page that I recommend. It's called the Kernel Cookbook. And it has a list of standard kernels and these little cartoons showing the sort of, okay, samples from that sort of, if you define your prior using only that kernel, what sort of function forms would you sample from that prior? So you have the squared exponential. Then you have what's called the rational quadratic kernel. And this is a bit like what we were discussing, because this is a kernel you get from taking the squared exponential, taking many squared exponentials with many different length scales and summing them. So then you get this rational quadratic kernel. There's this periodic kernel. So not surprisingly, there's a sine function appearing there. It has a length scale, but it has this hyperparameter p that sets the period of the function. You have something called the locally periodic kernel, which is the periodic kernel multiplied with the squared exponential. So what this is saying is a sort of, okay, local is periodic, but I'm still allowing the function to change gradually over length scale set by this L. You have the linear kernel, which is typically something you will include if you expect your true function to have some sort of linear trend. It might do all sorts of wiggles, but perhaps it has a linear trend running underneath it. You might want to use the linear kernel. If you define your prior just using the linear kernel and you do Gaussian process regression, what you're doing is Bayesian linear regression, right? It's equivalent. It's then a computationally expensive way of doing Bayesian linear regression, but it's conceptually the same. And a nice thing is that if you take two linear kernels and you multiply them, you get a sort of second order polynomial kernel. And you can do sort of, instead of Bayesian linear regression, you can do Bayesian second order polynomial regression, third order polynomial regression, et cetera, et cetera. So you can use this to generalize Bayesian linear regression. A key point is that kernels can be combined. And typically, so what you require, because the covariance function, no, the covariance matrix, which this function populates, right? This function just populates the elements in the covariance matrix. And because the covariance matrix has to be symmetric, the kernel function has to be symmetric under interchange of the input arguments. And the fact that the covariance matrix also has to be positive semi-definite, that puts restrictions on what are valid kernel functions. But what you can do is that you can, for instance, take your kernel function to be a product, sorry. So if you have two valid kernel functions K1 and K2, you know that the product will be a valid kernel function. And conceptually, you can think of this as multiplying as sort of the AND operator. Because what this is saying, like, for the covariance between f and f prime to be large, then both these kernels K1 and K2 have to be large, right? So it's sort of kernel 1 and kernel 2 has to be large numbers for the covariance to be large. So this is, think of it as AND operator. You can take the sum. And then for the covariance between f and f prime to be large, then it's sufficient that one of these are large, right? K1 or K2 is large. So think of it as the OR operator. And you can also do complicated stuff like saying, I have a kernel and I'm going to use some sort of, insert some sort of function of x as my new input. So add some sort of an additional layer of a function. I have no idea what that would correspond to in this sort of operator language. But typically what people end up doing is using the sort of base kernel, like squared exponential, like linear, like periodic, and you multiply them and add them, and try to construct a kernel that expresses the sort of function forms that you expect, that you have some prior belief in. Yeah. Yes, exactly. Okay. Let me just scroll down. Yeah, so this page, this kernel cookbook page, has then some examples of combining kernels. For instance, linear times linear gives you second order polynomials. And just to illustrate this difference between the sort of AND and OR operator, imagine you have a two-dimensional space and you say, I'm going to multiply two kernels like we discussed. If you do a product like this, one for kx and one for ky, and use a squared exponential, then for the covariance or kernel function to be large, right, the two input points have to be close, both in the x direction and the y direction. So this is just, if you look at this, the axis here is difference in x direction, difference in y direction. If instead you add them, right, you get something like this. Now, to get a large covariance, it's sufficient that one of the distances is small, either in x direction or y direction. Okay. So this is very much the art of GP regression, is constructing kernels. Though for a lot of use cases, doing something like, okay, just take the squared exponential, just take the Matan kernel, that might give you good results for many cases. But the sort of the true power of this is the ability to be more specific than this. Now, let's do a quick discussion of noisy data, because this is a point of confusion. So far, we have assumed that we have noise-free data. We have assumed that our training points f bar, f vector, are are samples of the actual true function. So far we have looked at noiseless training data, and that gave us a posterior of this form: P of f star given those noiseless training data, f vector x and x star. And in the case where you take your test point to go towards one of the training points, then your posterior prediction just becomes a delta function, right? Because it's just saying, okay, you're moving towards a function point where you actually know, and at that point you have zero uncertainty, because this is a point you know exactly. But we need to allow for uncertainty in the training data. And as we do that, there will be two different forms of our posterior that we should try not to confuse, because confusing them means that we will misinterpret our prediction uncertainty. So, and one of the things that I think makes this more confusing is that a lot of introductory texts to Gaussian process regression start by framing this as a method for working with noisy data. It's sort of the first case is saying, oh, this is a great method for working with noisy data. I think it's a great method in general, and noisy data is a special case. So now assume we have data on this form. So a training value yi is now defined, well, it's per definition y at training point xi. But what this means is the true function value plus some noise, epsilon. And this epsilon noise is a random variable, and it follows a normal distribution with zero mean and some noise level, some variance there, right? So all our points are sort of centered on the true function, but then with some noise on top. I will refer to this as being noisy, but keep in mind that it doesn't actually have to be any randomness involved. This could just be an expression of you being not completely certain about your training data. And you could use this epsilon just to say, I have some training data, but actually I don't have them. Yeah, I don't think they accurately or completely accurately describes the true function. So that normal distribution could just be your Bayesian expression of uncertainty. But typically we'll just refer to this as noise. And I think now, and this is the thing that confuses people, is that now we must distinguish two posteriors. The first is this one, where you are still making a posterior prediction for f star, but is now given some noisy training data that you learned and input points. And the other is where you're not making a prediction for f star, but you're making a prediction for y star. And the difference here is, in the first case, you're saying I have noisy data, but my posterior still expresses my degree of belief for the underlying true function at an input point. Now, that does not mean that if you then make a new noisy measurement at x star, you don't necessarily believe that that noisy measurement should be very close to your predicted f star, because you're predicting the true underlying function, and you do expect data points to be scattered around that true function. So in this first case, your prediction uncertainty expresses an uncertainty in the true underlying function. So if a data point then lies, say, 4 or 5 sigma away, standard deviations away from your f star prediction, right? That's not necessarily wrong at all. That's not necessarily bad. It just means that at this point, probably the amount of noise in the data completely outweighs your uncertainty in the true function, right? The other case is the case where you're saying, actually, I'm not going to make a prediction for the true function. What I will make a prediction for is, within what range do I expect a data point to appear if I make a measurement at x star, right? At input x star, where would I expect a noisy data point y star? And in that case, your uncertainty band should account for your expected noise level. So in that case, if you make that measurement and find that it's 5 standard deviations away from your prediction, then that is a sign that probably you have underestimated your uncertainty in some way. But keeping these two distinct is really important. And in practice, we get case 1 if we only add, let's say, call it noise variance, to the training set part of the covariance matrix. So what this means is that we take our old, so remember that this sigma was the part of the covariance matrix, which is just the training data. And we take that and we say we are going to add a noise variance along the diagonal, right? And if you do this, then you have this first case where you have allowed noise in the training data, but you're still making a prediction for the true function. We get case 2 if you, instead of just adding it to the sigma matrix, you add it to effectively your covariance function. So if we add a noise variance to both this capital sigma and k x star, which is your prior variance at the input point. So that's saying sigma goes to sigma plus noise variance times identity matrix, and k x star goes to k x star plus sigma epsilon. And I will not rewrite these, but let me just scroll back to these equations, right? Which were the central prediction equations for GPs. So mu star is our central prediction. Why did this happen? Interesting. Okay. So imagine I did the first case, right? I only added this noise parameter, this noise level to the sigma matrix, right? Then it only enters here. So then this would be sigma plus this variance times the identity matrix, and that entire matrix inverted. But if I added it to both places, then it would appear here and here, right? Then I have a noise term there as well. So there you see that in the second case, you are effectively inflating your prior variance with the expected noise of the data. And that is what gives you then your posterior prediction is no longer for the true function f star, but for a noisy data point at x star. If that made sense.
So I think that noise signal is from the dynamic matrix, right? Because that guarantees that it's like this inverted.
Exactly. So one of the one of the challenges in GP regression is the numerical challenge that this matrix has to be invertible. And even though it might in principle be, it might numerically be difficult to do it by adding this little, what's called a nugget term along the diagonal. By doing that, you're making sure that each column in that matrix is more and more different from the other one. And that makes your matrix move away from being singular, away from being non-invertible. So very often, even in the case where you think you are working with completely noiseless data, it's very common to still add a little bit of noise just to stabilize the numerics, and you'll find that that helps. What is also then common to do, especially in this case, is to treat this as another hyperparameter, right? And saying I'm going to optimize this parameter in my maximum likelihood fit, just as the other all the other hyperparameters. And what this does is effectively what you're trying to do is you're trying to learn the noise level. You're trying to learn from your training data. You're trying to learn what's my average noise level. But by doing that, you should keep in mind that now your posterior has suddenly become a posterior for noisy training data. And this is the case where we end up with the sort of the classic example of hyperparameter space having at least two optima, right? And hopefully I have that. I think it's further down. Right, so look at this example. It's the same set of data points. They're noisy function. There are no noisy data points around the true function, the blue function. And then the yellow function is the GP. And in the upper case, what's happened is that the GP has just inflated this noise parameter and say, oh, this looks like all the data, looks like the noise level in the data is just really big. So I'm going to assume I'm going to predict a flat function with a huge uncertainty. In the lower case, it has actually captured a function and then correspondingly said, actually, the noise level wasn't that large. And so this first case is a case of, so this is just a squared exponential plus this noise term. So here is a long length scale and a wide and a big noise term. And this is a shorter length scale and a smaller noise term. And if you look at, this is a plot of the likelihood function across this hyperparameter space. So the y-axis is the noise level, the x-axis is the length scale, and this is the log likelihood function that you're trying to optimize to fit your hyperparameters. And you see it has a global best fit point here, which corresponds to this case, which is the one you probably wanted. But then it has this wide range here, which also gives you a decent fit. And in this local region of hyperparameter space, it's the local optimum, right? And that gives you this case. So that means that you should, when you do this, you should worry about whether you found the global maximum in hyperparameter space, which means that you, if you use some sort of gradient descent method, for instance, you probably want to start your optimizer from a lot of different starting points, or you might want to consider some other slower optimizer, but that's better at trying to find global optima, like a differential evolution optimizer, something like that. For the last 10 minutes, my plan is to just list some interesting points and give you a couple of literature references. So the first point is that GPs equal infinite neural networks. What this means is that it's a well-known result and it's been generalized. I think the first result is from the early 90s. What this is saying is that, so you're familiar with the concept of a Bayesian neural net. Well, what a Bayesian neural net is, take a neural network and instead of fixing the hyperparameters, you say I'm gonna have a small probability distribution on each of my parameters in the network. And that means that, so again, it's just, okay, you're a Bayesian, so you express, instead of putting all your eggs in one basket saying this is the exact hyperparameter, you spread it out a bit. And that means that your prediction, instead of being one single value of your output network, your prediction is also a probability distribution over predictions. And it means that, for instance, you can take the same input to a neural network, and by sampling hyperparameters from your probability distributions, you sample outputs. So you can see that this starts looking very much like a GP. And it becomes mathematically, it becomes a GP in the limit where you take your neural network to be infinitely wide. So the first result was shown for a single layer, fully connected neural network with what's called independent and identically distributed parameters. So that's just saying that my PDF for the parameters should be the same PDF. And they should be independent of each other. So for instance, just apply a small Gaussian on all your hyperparameter values. In the limit where your network is infinitely wide, what you're getting is a GP. And what that's saying is just saying that the output distribution would be a multivariate Gaussian or just a Gaussian. And you can sort of, I think you can see why it makes sense. And it's effectively just a central limit theorem, right? That your neural network output is the result of a long sum of small contributions from all the different nodes and connections, right? but if each term in that sum is actually a random variable with some distribution, and they have effectively the same type of distributions, this is exactly the condition of the central limit theorem. And then the central limit theorem says that that sum should have a Gaussian distribution. So, so infinite neural networks become Gaussian processes, at least infinite Bayesian neural networks. And this has then been generalized to also deep networks, not single layer networks. So it's interesting, and it's also sort of philosophically, it's why some people prefer to refer to GPs as not as non-parametric, but as infinite parametric. Because you're in the limit where you had a network with an infinite number of hyperparameters, and suddenly it became something analytically tractable that you can work exactly with, which is kind of cute. So working with an infinite number of parameters is apparently easier than working with just a lot of parameters. So that's sort of philosophically and conceptually interesting. Then I won't write out all the details. It's in the lecture notes that I will upload, but it's what I call systematic underestimation of uncertainty. And the reference I want to point you to here is archive.org, and it's this paper, 1606 03 865. And this is exactly the point that we discussed earlier in the lecture, how the fact that usually in GP regression, you choose your hyperparameters by doing a maximum likelihood fit. By doing that, by being non-Bayesian in that sense, and by being quote unquote inconsistent in that sense, you end up actually underestimating your uncertainty. And what this paper does is saying, well, you could do it the fully Bayesian way by doing that integral, as we discussed, but actually here's a quick method to sort of compensate without doing that integral, but compensate for the fact that you're underestimating this uncertainty. And I will show you sort of money plot from this. I think I have it here. Or perhaps I don't. No, okay. If you look up that paper, you will see that effectively what this says, say I have some data points like this, and my GP goes, so I learned this stuff. I have some uncertainty band going around here. But then I run out of data and I extrapolate, right? And then following the usual method, your prediction would fall down, say you had a 0 prior mean, and the uncertainty band would take some constant, just get your prior variance. But your uncertainty will not increase even though you move further and further and further away from the data. But by taking into account this correction that they discuss, which is effectively saying you learn the hyperparameters from the data, you estimated the hyperparameters in a maximum likelihood fit, but that estimate comes with an uncertainty. So you should take into account that. And that means that this uncertainty band will gradually increase as you move away from data, which is more sensible behavior, probably. Then it was the point that we discussed, regularization of covariance matrix, which was what we discussed that, you need to, for this to be numerically invertible. So it helps adding a little bit of noise. And a trick here is to keep an eye on the keep eye on the condition number of your matrix. So that's kappa of your matrix sigma. And the condition number is just a ratio between the largest eigenvalue and the smallest eigenvalue of this matrix. And for a singular matrix, this goes to infinity. So sort of as the condition number increases, you can expect to get more and more numerical problems. And then by adding some noise along your diagonal, you can lower this condition number again. So you can use this condition number as sort of just track whether you're approaching a problematic limit. And you can try to say, for instance, say you realize from experience that as long as the condition number is below this threshold, things seem to be working. That means that you can test this and see, oh, now I'm getting into a problematic region. I'm going to increase the noise a little bit to go down again. There was one more thing there. Yes, and this problem typically gets worse with more data, right? Because the more training data you have, the more probable it is that two data points are very, very close together. And once two data points are very, very close together, that's when two columns in your covariance matrix start becoming more and more equal to each other. So your matrix starts looking more and more singular. But then adding this little noise term to the diagonal means these two columns get contributions at different elements and they're pulled apart effectively. And finally, how to deal with the large data limits. So I said that vanilla GPs sort of start failing for computational reasons once you get order 10,000 points. So how do we deal with this? And this is a big, big topic of research. So you'll find hundreds and hundreds of papers discussing things like this. I will just list some examples of things that I've either used or seen. But the general approach in a lot of these is saying, okay, we have trouble inverting an n by n matrix when the matrix is too big. Let's try to overcome that by either making the matrix much more sparse, so you end up with a sparse matrix, or perhaps we can divide our data so that effectively we get a block diagonal covariance matrix. So each block then would be sort of an independent GP, and they're just stitched together in input space, things like this. So there's one approach called distributed Gaussian processes, and this is archive that I've used in the past, and that seemed to work well, at least for the case we were looking at then. 1502.02.843. And that's effectively saying, I'm going to divide my data into multiple batches and train GPs on them separately and then combine GPs afterwards. Then about that combination step, there's a method called generalized, this is a terrible name, generalized robust Bayesian committee machine. I mean, I've read this paper multiple times, so I'm still not sure if I actually understand all the words there. But it's effectively saying that, okay, if you have a bunch of Bayesian estimators like this, your final joint prediction should be sort of a committee decision. So it's a rule for how to combine them and appropriately taking into account the additional uncertainty coming from the fact that you had multiple estimators. So this is 18.06.00.720. There's a lot of work and a lot of papers on what's called sparse Gaussian processes, which, at least to my understanding, is effectively saying, instead of using all these input points, I'm going to replace many input points with a few well-chosen input points. So it's using what's called inducing points and saying that, okay, using a few well-selected points will almost contain all the information that I would have in having a lot of random input points. So making the covariance matrix much more sparse that way. And then there's a very interesting approach. I haven't used it myself, but I think it's sounds super interesting. So I want to tell you, I'll give you the reference. It's called deep kernel learning. And there's many papers on this, but I think the first one is this 15.11.02.222. And what this is doing is saying, okay, GPs are not very good at handling large data sets, but neural networks are. Can we use our training data to train a neural network to be the kernel of a GP? Because then we are sort of learning an optimal, a very flexible, but we're learning a sort of optimal kernel function for this specific problem with this specific data, right? And then using that network to be the kernel of your GP. So then the trouble of using a lot of data then becomes training this neural network, but you don't have to invert a gigantic n-by-n matrix anymore. Apparently with this method, I think this paper has examples where they use this with data sets of millions of points, right? Which would be unthinkable with vanilla GP methods. So this is certainly an interesting topic. And that's it. That's all I wanted to say about GPs. Yeah, questions?
I guess, can you not fix this in a kind of dumber way by changing your, so for any number of points that you have sampled, you can always make your kernel tight enough, yes, to avoid singularity, right?
What do you mean by tight enough? Am I not?
I guess, yeah, so if you have the radial basis function kernel, then you can change your length scale to be short.
Yeah.
And then you wouldn't, close points wouldn't be.
Yeah, I see your point. But so that would solve the problem of the matrix being singular or being close to singular, but it would not solve the fact that you still have an n-by-n matrix that you have to find the inverse of. Right, which is just then it's computationally doable, but it's just so slow, right? And that was the starting problem, that in the case where training your GP becomes slower than evaluating the true function or performing the experiment or whatever, at that point there's no gain left.
Okay.
Yeah. But you're absolutely right that would solve the, I think.